Hello, everyone, and thank you for joining this session. Before more people arrive here at this presentation, and until Vasil Momchev joins, who is the chair of this session, I will just quickly go over some housekeeping details. At the end of this session, we have planned a short Q&A in which Thomas here will be answering your questions. So make sure to drop them in the chat so he's able to see them and hopefully answer them. With that, I see that Vasu has joined, so he will handle the introduction from here. So Vasu, up to you.
Hi again. Okay, this is yet another time you see me. And today's talk will really cover this property graph versus RDF model. I know that this is a religious dispute and there are many die-hard supporters. So, no, we're not going there to say what is better or worse. And the focus of the next talk is basically subjectively understand what are the missing features in the RDF model which exist in the property graph model. After the introduction of the RDF star, I was thinking that everything is supported, but probably not. What about the graph path search? And Thomas is our GraphDB lead software engineer, and he will have the task today to walk you through the graph path search problem first. What is the missing bit of functionality in SPARQL, and how the different vendors overcome this functionality? So today's topic will be basically on top of GraphDB, and how you can pass all the LDBC consortium tests, which are not only for RDF databases, but also for property graph with a single graph database engine. Welcome, Thomas. The broadcast is yours.
So, hi everyone. Hopefully you can see my screen. So today, as mentioned by Vaso, I will be presenting the new GraphPath search functionality in GraphDB, which is available since GraphDB version 9.9. Before we go into a bit more detail about the functionality itself, let's have a very short introduction into what graphs actually are. So graphs can be represented as discrete data structures that are composed of sets of nodes, or also known as vertices, and the relationships they actually form. This allows graphs to be very versatile in terms of the structure they represent, and to also have the chance to show very complex and difficult to traverse relationships. RDF is an example of such a graph model. It can be described as a directed multigraph that actually supports not just only loops, so that would be resources that reference themselves, but also multiple edges between pairs of nodes. In order to be able to officially find paths and relationships between those nodes, we need to use some kind of order. And this order of traversal is actually brought by the graph search algorithms. These algorithms don't just specify the order of traversal, they actually help us in finding explicit resources or just traversing an entire graph. An example of graph search algorithms include the depth first search and breadth first search algorithms, which are basically the bread and butter of the graph searching algorithms. So what is the difference between graph search and pathfinding algorithms? Well, pathfinding algorithms can be seen as an abstraction on top of the graph search algorithms, as the graph search algorithms are actually the backbone of pathfinding algorithms. Pathfinding algorithms can be used in order to find and display relationships between two nodes. They can be used to express the connectivity of a given resource, and it can be used for many versatile tasks, including finding all the possible paths between two resources or more, and displaying the actual shortest path for them. As I've mentioned, pathfinding algorithms are built on top of graph search algorithms, so we will take a closer look into what are those main graph search algorithms. Well, as I've mentioned, the two most important ones include breadth first search and depth first search. But the reason why we talk about them today is because they've both been added as implementations inside our GraphPath search functionality, where breadth first search is used in a more of a level by level traversal manner. It is usually implemented with a first in, first out queue, and usually because of that, it requires a lot more memory, since the fact that when we are traversing adjacent nodes, we actually have to store them in this queue. Due to this reason, memory consumption is of course higher, but it also allows us to find more quickly in the average case scenario the shortest path between resources, and also to be able to discover actual graph connections. Both the time complexity for breadth first search and depth first search is the same in their worst case scenario, which is the number of vertices plus the actual number of edges. While depth first search has the same worst case scenario, it also provides a different type of traversal, which is also guessed by its name. It's based on the idea of backtracking, meaning that we start from a given node and we traverse to the last possible node in a given direction, and from there on we go one step back and so and forth until we actually traverse each path possible. This algorithm has very limited use cases, but it is very efficient to actually use in terms of storing the entire possible path in memory, because of the fact that it's usually implemented with a last in first out stack. Due to this reason, we use both algorithms. We use the breadth first search, of course a modified version of it, in order to parse an in-memory graph where we search for the shortest path to a given resource. And after we parse this in-memory graph, we actually use the depth first search in order to return each possible path. I'll speak about this more in a second, but first let's look at why are we actually looking for these paths? What are the main use cases behind it? Well, one of the possibly most popular use case is, of course, road navigation. Every time we input a given destination into our GPS, we're basically doing a short path search algorithm that is based on given weights due to the distance between different roads. Other very interesting use cases include knowledge graph analysis, which basically allows us to discover relationships between resources and the dependencies they form in order to better gain an understanding of the dataset itself. Furthermore, we also have use cases such as supply chain analysis, which is a very interesting one where we can build a digital fabric that actually follows the real life scenario of the supply chain. And we are able to not just analyze, but also discover relationships between factors and events that actually affect production or supply. Similar use case can be seen in causality mining, where we can analyze events and symptoms in healthcare sector, or also analyze trading signals and financial information in the financial sector. Other use cases include the recommendation engine and last but not least, the social network analysis. For today's demonstration of how the graph path search actually works, we'll be using the social network analysis use case, which is based on the social networking benchmark. Before I delve into a bit more detail about the social networking benchmark, I would first like to say a few words about the linked data benchmarking console, which is a TPC-like body that actually defines standard graph benchmarks that basically aim to foster and improve the performance of various query engines, and members include Ontotext, so that's us, Neo4j, AWS, Oracle, and so forth. As I mentioned, they have a number of standard graph benchmarks, and one of those benchmarks is actually the social networking benchmark, which is basically the de facto standard for property graph databases. It is a very analytics-oriented benchmark that mimics the performance load of operating an actual social network, and it has numerous benefits in terms of analyzing how graph search algorithms and path search algorithms actually operate. For this reason, we've used it in order to make sure that our implementation is not just theoretically sound. So we've checked not just in terms of theory how our space and time complexity actually works in terms of pathfinding algorithm, but also to compare this with actual real data and make sure that there aren't any inefficiencies or choke points in terms of the implementation. And on this note, we are very proud to say that with the path search functionality, we actually successfully passed the benchmark, and we are the first actual RDF database to do so. We are currently waiting for the LDBC consortium to actually officiate these audit results. And let's have a closer look into what the actual person data model is. So as the social networking benchmark data model is based on information about people, we'll mostly have information such as basic data about people, such as first name, last name, where they're located, where they work, and what they study. And we also have elements which are more commonly associated with social networking, such as comments and replies of comments and so forth. On a separate note, the SMB data generator is very sophisticated, and it provides not just realistic but also challenging data distribution. And for that reason, it can be used to test the functionality at different scales. So it can be used to be tested small, or large, or medium scales in terms of various node degrees. And for that reason, it makes it the perfect benchmark to check the actual performance of the path search functionality. From the interactive data set, we'll be using today two subqueries that actually use the path search algorithm in order to show you how it actually works. So the first query is based on the idea of friend of a friend. So we'll be looking from a starting person ID, how many people he or she is actually connected to by at most 3 steps. For our second query, we'll be doing a short path search between two people with actually given IDs. But before we go on and see how we can use the graph path search functionality, we'll actually see first why we needed to implement it. So there, as you can imagine, SPARQL and RDF are very powerful technologies. Using SPARQL, we can describe resources very efficiently, but RDF as a technology and SPARQL are not so efficient in terms of describing paths and relationships between resources. As you can see from the extract here, which is basically the first SMB query, but written with plain SPARQL, we can see that in order to do the friend of a friend search starting from a person with ID 103, we need to provide 3 separate subqueries combined through union patterns, and then on top of that we need to filter those results in order to make sure that we are not receiving any duplicate results. For that reason, we can see that this kind of syntax is very rigid and is complex to write even for advanced users. The numerous subqueries and filter and union clauses can actually put even more pressure on the query engine than usual, and for that reason they are very inefficient. So the query writing on one hand is an issue. The rigid structure of describing resources is also, in terms of RDF triple patterns, is rigid. And we have a different limitation, which is the tabular result format of SPARQL. Due to the lack of indexation in SPARQL and the fact that we have to bind by hand the distance between the different paths, we must be able to write very long queries. And for example, imagine that currently here in this extract we have paths with length 1 and 2, but if this path length reaches 15, we will need to have almost like a second table where these results would actually be showed. So in this kind of examples, we would have rows where there is a single column, and then another one where there will be 15 fully filled columns. For that reason, the tabular format and the fact that we have to bind indices ourselves, graph path search is not very efficient with plain SPARQL. Another limitation, of course, is the fact that, for example, property paths that have been added since SPARQL 1.1 as a syntax functionality actually help us with the reachability part of the queries, but don't actually allow us to analyze the path itself. So we can see that two resources are connected, but we cannot explore the relationship itself. So let's see how we can actually implement this query using the graph path search functionality. So in order to do that, we just need to specify a special service extension, which is done with the magic predicate path search. But before it, we need to bind the actual source with the and in order to find the friend of friends for this person. So here we can see that we've bound the source as ID 103. And after we specify this service clause, inside of it, we need to specify the different parameters in order to make sure our search is correct. So we're looking for all the possible paths starting from this node. Keep in mind that the graph path search functionality has four main functions. These include all paths, shortest path, shortest distance between two resources, as well as finding cyclical connections. So for the all path search, we can define source and destination node. So for example, if we have both source and destination nodes, we will be looking for all the possible paths between those two resources. But if we don't bind the destination node, we'll be looking for all the different resources that person with ID 103 is actually connected. Due to this, we can actually see the connectivity of the resource itself. And for example, here we've also added these two parameters, which are the result binding index and the path index. So the result binding index actually helps us to understand which edge or which resource comes after which inside each path in order to better follow the result set itself. Also, we have the different path indices here, which actually allow us to differentiate the different paths inside the result set, as there can be more than one using such queries. Also, as we are currently looking for at most friend of friend of friend, so that would be maximum path length of 3, we will be specifying this as a query limitation. And as you can see here, we also have a very special nested service. This service must have the same ID as that of the pathfinding function. And basically, what it's used for is to define the kind of relationship resources in the graph must have. So it will only evaluate recursively using the level by level approach of breadth first search uh, only through this kind of relationship. So for example, here we've bound the source as person with ID 103, and what would happen is the graph path search functionality would bind it as the start node and evaluate it recursively until we have reached maximum path length of 3. And then after we've parsed this in memory graph, we would actually return each different path separately. So let's see how the actual result looks like. As you can see here, we're only looking at the people we can connect to by different steps. So as you can see here, we have the different path indices. So as you can see here, we have 7 different paths, as the indexation in graph path search starts from 0. Also, we have the index inside the path, so we can actually see which resource comes after which. For example, here we have path with length of 3 and path with index 3, sorry. And we basically have a relationship where person with ID ending in 103 is connected to person with ID 601, and after that person with ID 086. Keep in mind that currently we just wanted to see the edge and nodes rather than the entire edge of the path. For the next query, we'll be actually looking at the entire edge inside the path. And yep, let's take a look at how this is actually implemented. So here again, we have a path search function defined as a service clause. Again, we need to specify the ID, but here this time the ID is different. So we don't have the all paths function, we have the shortest path. Here we're looking for the shortest path between person with ID 103 and person with ID 168. So we've bound the source and destination, we've added their source nodes here and destination nodes respectively, and we've also included the indices in order to better understand the actual result set. And apart from that, as you can see, we don't specify any start node or end node, meaning that we don't care about this simply just the start or end binding of each edge inside of a path. Other than that, we want the entire result binding, meaning that we want every single edge inside the path itself. And as you can see, we don't have a nested service clause. So what this means is actually we don't know what kind of relationship these two resources might have or might not. And for that reason, we would just want to use a plain subject predicate object pattern in order to actually find any possible relationship between them recursively. Furthermore, when we use this kind of pattern, we can actually see the predicate connecting those resources because it's just a single triple pattern. And we've also added a flag in the end, which is actually specifying that we don't just want to see the subject predicate object relationship, but we also want to see the object predicate subject. So that would be the reverse relationship followed in order to reach any sort of connection between those two resources. Keep in mind that by default, GraphPath search is used with directional search, and the bidirectional flag is actually available since GraphDB 9.10. So let's see how the actual result looks like when it's parsed as an RDF star statement. So as you can see from the extract here, we have a path with length 4, as the last index inside the path is 3, and this is just the first path, so that would be index 0. Again, we parse each edge inside of the path as an RDF star statement, and here you can see we start with person ID 103, and then we end with person with ID 168, and the relationship they form actually comes from a comment that is actually the reply of the comment commented by created by person with ID 168. And as I've mentioned, when we use the wildcard predicate pattern, we can actually see the predicate connecting these resources. Keep in mind that when we use graph patterns, we don't actually see the predicate because even when we use the RDF edge star label, because it's not available. So we might specify a very complex relationship. It might be direct or it might not be direct. So for example, we can specify an n-ary type of relationship. And in that case, we won't have a direct predicate connecting those two resources. Therefore, when we parse this kind of information using RDF star edges, we actually specify a magic predicate known as connected to in order to represent the relationship as an RDF star statement. But this is a kind of limitation because we might want to know, for example, there might be actually a predicate inside the graph pattern and we just might wanted to add some other filters, or we wanted to negate some predicates, and etc, etc. And for that reason, in GraphDB 9.10, we actually added the exportable bindings. So this functionality actually allows us to propagate values outside of the nested graph pattern, which can be seen here, and into the result set. So what happens is when we have this kind of queries, rather than just simply evaluating the graph pattern and saving the in-memory graph as purely edges, we attach to each edge the extra metadata that we actually want the user to see. So as you can see here, we have again a standard SPARQL query, and inside of it we have the path search service, and we've bound again the source and destination nodes. So here we are starting from person with ID 933, and we want to find all the possible paths to person with ID 474. Here we've bound the source and destination. We have the start and end nodes, which are necessary in order to describe the relationship, the recursive relationship that the graph might have. And we've also added the indices in order to better understand the results. We've also added these three exportable bindings. So as you can see here, we want to know the date those people actually met. We want to know the name of the start node. So that would be the name of the person and the name of the second person to which he is connected to. So to whom he or she is friend. And as you can see, we've also specified them inside the graph pattern itself. So let's take a look at how this result actually looks. So as we're interested in seeing the names, we've selected them as the only bindings to be seen in the graph query. And here you can see that Mahinda is connected to Ning through 7 other people. And this path has length of 8, and that is just the first path. We can also see the date at which they met, and we could also add any other information from inside of the graph pattern, which we might be interested. And one of the main reasons we actually did this is because uh, we wanted to simplify the operation of actually finding metadata about each edge, so that you don't have to write 2 or 3 separate different queries in order to find more information about the path itself. Keep in mind that the exportable bindings do not necessarily have to be binded. I mean, they can be put inside optional blocks, or they can be added in unions, and they can be left blank in different binding sets. So let's take a look at how this SPARQL to property path translation actually happens. So in order to take advantage of the GraphDB query engine and the entity pool in order to save memory, we've actually integrated it inside the engine query model. And as I've mentioned before, we provide 4 main functions, which include finding the shortest path between resources, finding all possible paths to, from, and for between 2 resources, finding the distance between 2 resources, and finding a cyclical relationship. We support wildcard path search and the more targeted version of the graph pattern, where the graph pattern can be, as I've mentioned before, actually used to describe not just direct relationships between resources. They can be indirect as well. For example, they can be n-ary type of relationships. And we're very happy to say that the graph path search service extension is fully compatible with the SPARQL 1.1 service syntax, which allows for easy integration into queries, as both the format of the query itself is SPARQL compliant, and the result returned is actually RDF in terms of format. So also another very important thing is we can export any part of the edge of each edge inside the path. So that could be done as an RDF start edge, or it could be done separately as a subject, predicate, object, or all of those bindings separately. We also have, as you've seen from the second example, directional and bidirectional search, which can evaluate paths both directionally and by default. And if the path bidirectional flag is set to true, it will evaluate bidirectionally as well, which is applicable to not just the wildcard property path search pattern, but also for the more targeted version, the graph pattern. When used with the actual graph pattern, you can specify, when you specify the graph pattern, basically what happens is we do a union between the start and end nodes, and then we actually reverse the order in order to find bidirectional relationships using it, which allows a very robust and easy in-memory graph building, and for a very interesting interface. So let's take a look at this short diagram in order to better understand how the GraphDB engine actually does the graph path search. So here we have a standard SPARQL query, and inside of it we specified the path search service, and here we are looking for the shortest path between resources X and Y. And once we send this query over, GraphDB parses the path search service, validates the actual parameter specified inside of it, and based on it, we do unweighted breadth-first search recursively on the level-by-level basis until resource Y is actually reached. At which point, once we've built the entire in-memory graph leading to resource Y, we actually pass it over to the depth first search, which traverses this memory graph in order to be able to display each separate path. For example, we won't return just a single shortest path, for example, like XAKY, but it will also return all of those shortest paths that match that given length. So it would return both XAKY and XABY. So Finally, some more details about the graph path search technicalities. The different path search functions require at least the source and/or the destination to actually be bound. Only the cyclic function requires just the source binding, meaning that we don't need to specify destination binding as we're looking for circular references to the source itself. Furthermore, we don't need to use the bind as or values clauses in order to define the source and destination nodes. We can use other subqueries, which makes the SPARQL syntax for graph path search even more robust, as we can do an entire set of pairs of nodes in order to find their relationships and actually display them as part of the result set. Furthermore, we also have a separate parameter which can actually limit not just the maximum path length, but also the minimum number of edges. However, it is only available for the all-path search and for the cyclical search. And last but not least, we can also use, as I've mentioned before, the wildcard graph pattern in order to see the predicate that connects to the separate edges inside of a path, but also we can use the graph pattern with exportable bindings to achieve that same result if you want to add some more complex type of relationships. And also the path and edge indexation are both non-mandatory parameters, but they follow the Java indexing convention starting from 0, and they actually allow you to gain a better understanding of the paths inside the result set. So here is a short memory and market analysis of the different main functionalities that can be seen inside GraphPath search functionalities. And the four functionalities include SPARQL 1.1 compliant syntax, complex pattern and relationship definition, being able to find distinct paths between resources, not just a single path, and also being able to use wildcard predicate search. So that would include where we don't know whether there is any relationship between the resources and we just want to find whether there is any nested triple or any type of relationship that connects them. And we're happy to say that we support all of these functions, and we plan to develop even further our GraphPath search algorithm through these next stages, which include possibly in the future releases adding a minimum spanning tree functionality, as well as being able to use parallel path search in order to traverse larger data sets more quickly, and adding further query processing and data structure optimizations in order to improve on memory efficiency. So that's from today's presentation about GraphPath search. Now let's do a quick Q&A session. Thank you.
Okay, fantastic, Thomas. It was really a lot of information. You did, however, an excellent job to communicate it. I just want to outline some highlights we have seen. Yes, SPARQL, it's possible to do graph path search, but it's not convenient. So this new feature is actually a syntactic sugar, which makes the graph path search much faster and easier to write because you have a just simplified syntax, as you have seen. And the other highlights I wanted to say is that yes, an RDF database can pass a property graph benchmark. It's not a challenge. And as far as I'm aware, we are also in discussions with the LDBC Council in order to have an officially audit results where to cover not only the functional aspect, but also the measurement and the non-functional aspect, how quickly an RDF database can pass a property graph test. Sadly, that we will not have on the Neo4j or some of the other property graph databases officially already test, but let's see, maybe this will change in the future. And the other things to outline before to go to the questions is that yes, actually reasoning it makes can also sense in the context of the property graph databases. This is something not shown, but some of the queries we have seen that if you use the indexing, inference actually is indexing, which is a special form of indexing, you can also improve their performance. And yes, indeed, RDF star, like one of the questions, simplifies the model and make it much more efficient, time efficient in terms of the loading time. So maybe we can go now to the questions. Actually, there was a discussion how does the catalog of algorithms built in compare to other solutions. And in the discussion, we found out that actually you can integrate any type of algorithms next to the data using the plugins. And then I think, Thomas, you answered that how the graph path search algorithms, the uh, the shortest path and all the path search are executed, that this is a breadth first. Maybe the other is interesting. Is it possible to have directed direct directed results, edges, returned by unidirectional path search?
Yes, of course, this can be achieved through the graph patterns, where, for example, if we combine, let's say we have a standard pattern of a subject, predicate, and object, it can be done through a union with the reverse order, where we specify the binding of the predicate as P1, meaning that if we export those two bindings through the export binding functionality in GraphDB 9.10, we can also see which edge is reversed and which edge is in the standard order. Therefore, both of those can be seen as part of the result set. And if we don't care about the direction of the graph path search, we can just specify the bidirectional flag set to true, and it would return the standard order of the path. So that would be starting from resource 1 to 2, 2 to 3, and so forth until the actual final result is reached or the graph is actually parsed.
Okay, so the next question is, these searches go hand in hand with visualization. Are there any Ontotext React JS libraries for this, or are there any other supported libraries open source?
There are a number of possible libraries that are available out there, but if you use a construct query, you can also do a graph path search inside the visual graph functionality of our workbench. Furthermore, we are actually planning to support this kind of visualization in GraphDB in later versions, where we will be using the graph path search functionality through a separate interface. So you would be able to specify just the nodes and the type of relationships, and that would be visualized as well. But in terms of libraries, I could think of also Go.js is a very interesting one. And in order to use it, you just have to take the result out of the RDF, parse it as a JSON, and you're good to go.
Absolutely, and I can add that Visual Graph already supports this visualization. Of course, this is purely on the RDF data model. You are going to display the nodes, and very often our experience with visualizations is that you need a higher level processing of the data, what type of nodes you want to render. And also there is a partner product, Metafactory of the Metafax company, which you saw today, basically, which has nice interface to demonstrate the visual search and how the things are connected. So yeah, it's absolutely a must. I agree, Maxim, that this is a must feature for the graph path search. So a final comments, we have ended this track, and the last event from the Knowledge Graph Forum conference is the panel, which will take roughly in 1 hour time, and it will be an interesting challenge where we're going to get actually in this forum we had technology providers, clients, business cases, and now it's time the system integrators to talk whether they have all the functionality and features to deliver knowledge graph solutions to the business. Actually, it will be an interesting panel, and see you there in order to find out what is the maturity of the technology and what are the missing technology bits, or are there any other organizational or process challenges. Thank you for your time, and see you later. Bye bye.
Thank you, everyone. Bye.